Good morning, everybody. Today we're going to do redox reactions, and redox reactions are really important in everyday life. So you hear about iron rusting or silver tarnishing. Those are redox reactions. And batteries, how batteries work and how electric cars work. Also aging process is called oxidative stress. So a lot of these things involve oxidation and reduction reactions. In fact, that's what redox is. It's a combination of the two terms, oxidation and reduction. And this is abbreviated into redox. And the reason why is because oxidation and reduction reactions occur together. And that's because oxidation means a loss of electrons and reduction means a gain of electrons. So an element that loses electrons, those electrons go to another element, so that element gains electrons, and so that's why they're always paired. So for example, a mnemonic to remember that is oil rig. Oxidation is loss of electrons and reduction is gain of electrons. So oxidation is loss, reduction is gain, so that's right here as well. So that will hopefully help you keep those processes defined, remember the definition for those. These are chemical equations which represent an oxidation and a reduction. So if oxidation is loss of electrons, this is an example of that. Sodium, with its one valence electron, since it's in group 1, it's going to lose an electron, and then that means that electron comes out right here. If you see an electron on the right side of the equation then, that means it got lost by what you started with. So this is loss of electrons. So that's an example of oxidation, is loss of electrons, oil. Okay? And then over here, magnesium ion, it already lost its electrons. It gains electrons to become magnesium atoms. Magnesium atoms have these 2 electrons because it's in group 2. So ions do not have those electrons. The atom does have those electrons. So what we're doing here is we're gaining 2 electrons. And when we gain electrons, that's called reduction. Reduction is gain of electrons, and that's how we get rig. So oil rig is a really handy device for remembering what's getting oxidized and what's getting reduced. So electrons that appear on the product side of equation 1, that means that sodium lost electrons. Electrons on reactant side, so left of this arrow, means that we've gained electrons. Equation 1 is an example of an oxidation because we lost electrons, so oil rig. And then equation 2 is our reduction because reduction is gain of electrons. And you can see how they happen together because if sodium loses electrons, something has to pick that up. So that's why we call these redox reactions because they involve both of these processes. Okay, some reactions are redox and some are not. So easy way to tell if you have a redox reaction or not is whether you have one of these types of reactions that we covered in class. So if you have a synthesis, decomposition, single replacement, or combustion reaction, then those are examples of redox reactions. And what's the reaction that's not in this list? It's the double replacement. Double replacement is not an example of redox. So let's take a look at this equation and say, okay, what type of reaction is this? So of these types, is it synthesis, decomposition, single replacement, or combustion? So I'm looking at this as this is like A, this is B, C, and I have A, C, and B. So A and B switch places. That's an example of a single replacement. So I'm going to write single replacement in here. Is single replacement a type of redox reaction? Remember, these are types of redox reactions. So yes, it's a type of redox reaction. So I'll just put a little note here that yes, we expect there to be some kind of transfer of electrons because this is a redox reaction. So now, let's take a look at where those transfers occur. So write the charge of NaS and magnesium solid as 0 above their symbol. So this is sodium in its elemental form. So sodium with its valence electron, it's neutral, it's not sodium ion, and it's in its solid form. And so it says to write 0 because that's what charge it is. Okay, it's neutral. And so is this magnesium. There's no charge here. So this is 0. In actuality, these are called oxidation states, and they're pretty similar to their charges. You could pretty much get them from their charges often, in intro level chem anyway. Okay, when sodium, oh yeah, now it says write the charge of magnesium in its compound, and then do the same with sodium in its compound. So here's the compound, magnesium chloride. What's the charge of magnesium in this compound? So if you remember from ionic nomenclature, so ionic compounds come together, opposite charges. This is some kind of plus charge, and this is a minus charge, and they come together. So magnesium is in group 2, so it loses 2 electrons. And then sodium is in group 1, so it loses 1 electron. And so those are the charges of those ions. So now I want to track what's happening to each of these. Let's take sodium. Sodium goes from 0 charge to +1 charge. And that means the electrons are negatively charged. So if you gain electrons, you gain negative charge. If you lose electrons, you lose negative charge. So you become more positive. Here we're becoming more positive. So we've lost electrons. So this is lost electrons. This is oxidized. So what we would say is that sodium got oxidized. Okay, let's take a look at magnesium. If you know sodium got oxidized, what do you know about magnesium? You should know already by default that it got reduced, because that's the only answer that's left. But let's take a look at that. +2, and we're becoming more negative. We're going towards 0. So that means we're gaining electrons. And gain of electrons is reduction. Okay, so one thing that I do to remember this is I make a number line, and I say 0 + 1 + 2 - 1 - 2. So I think of reduction as going lower in number, so lower from positive to negative, that's reduction. And if you go the other way, you go from negative to positive, then that's got to be oxidation. So that might be a nice easy way to figure out what's going on. We're going from 0 to +1 for sodium. 0 to +1, that's going up, that's oxidation. We're going from +2 to 0, +2 to 0, we're going down. We're reducing in positive charge. So that's reduction, okay? All right, so just back to these questions. Sodium ends up losing electrons in these equations, so it's oxidation. Magnesium gains electrons, so that's reduction. Now a couple of terms are coming up here. Okay, so first, let's get this part straight. Sodium is oxidized. Magnesium, 2+, is reduced. So let's write that down somewhere. Let's write it down right here. So Na is oxidized, not Na+, it's Na solid that we started with. Magnesium is an ion in this compound, so technically I need to write Mg2+, not Mg, because Mg is out here. That's a product. So Mg2+ is what got reduced. So sometimes you get questions like that. What was oxidized? What was reduced? Now here are some new terms for you. Sometimes we want to know how well something does at oxidizing or reducing something else. So for example, the species that is oxidized, so that's sodium, it's called the reducing agent. So reducing agent. Okay. So sodium is the reducing agent, and what does that mean? That means sodium is the agent for a reduction. So that means sodium is good at reducing something else. And when it reduces something, it's letting that thing gain electrons. That means it's itself losing electrons. Okay, so it's sort of crazy, but here's what that looks like. Sodium loses electrons, which means it's making this guy gain electrons by giving it its electrons. So it's good at reducing this other thing, right? And in that process, it gave up its electrons, so it gets oxidized. So whatever gets oxidized, it's good at reducing something else. So that's why it's called a reducing agent. A really easy way to remember is just whatever gets oxidized is the opposite in terms of what it does. So something that gets oxidized is good at reducing. Something that gets reduced then is good at oxidizing something else. Okay. So that would be magnesium in magnesium chloride. Magnesium 2+ is the oxidizing agent. Okay, so this is really useful when you hear the terms, antioxidant. So antioxidant is something that keeps something from getting oxidized. And for example, they say eat blueberries because it has a lot of antioxidants. What that means is the blueberries contain something that gets oxidized, and that prevents something else from being oxidized. So in other words, the anthocyanins and those dark pigments in blueberries that make blueberries really good to eat, or good for you, those antioxidants keep your DNA from getting oxidized. Instead, those anthocyanins and pigments are the ones that get oxidized. So that they have a protective effect. Okay, answer these questions about this reaction. So first, what type of reaction is this? Let's see if it's even a redox reaction. So this is AB and CD make AD and BC. So hopefully you can see that there are 4 things and they're both switching here. So this is called double replacement. Is double replacement a type of redox reaction? It's not really on our list up here. Double replacement was not in this list, so technically we predict that it's not a redox reaction. Let's work through it just to make sure. Write the charge of each element above its symbol. Okay, so in this compound, Ba is 2+, I can tell because of the periodic table. Sulfur will be -2. Platinum, I don't know, so I need to look at oxygen is -2. So platinum must be +2. Barium is +2. Oxygen is -2. So just based on their charges in the periodic table. Platinum, we figured out over here it was +2, so that carries over. And sulfur was -2. And actually, we wouldn't know what this was. We'd have to figure this out first and then know that it's +2. Because it may have changed, so I shouldn't have done that. Okay, write the charge. We did that. Do the charges change from reactant to product? So barium stays +2. Sulfide stays -2. Platinum stays +2. Oxide stays -2. So everything stayed the same. That means there was no transfer of electrons, and this is not a redox reaction. So as long as you see charges changing, then you know that's because electrons are shuttling around. Okay? Here, the electrons are not. These ions are just taking their electrons or lack of electrons and just pairing up with the other. So this guy here, barium, so for example, barium, what is barium doing? It's just saying, okay, I'm just taking everything here and I'm just going to meet up with this guy. I'm not going to actually transfer any electrons. I'm just reforming a compound with this. So there's no transfer of electrons, like they're just picking up their stuff and moving with somebody else. But they didn't actually do any transactions. Okay? So double replacement reactions are not redox reactions. So I'm going to say no. Now everything else is a redox reaction, so let's take a look. This is single replacement. So this is redox. This is synthesis because if A and B make AB, so these two come together to make a compound. So that is a type of redox. This is single replacement again, so yes. This is a double replacement because I've got NaCl, Ag, so acetate. So I've got 4 things here and those 4 things switch around. So that's double replacement. That's not redox. And then this last one is an example of redox. And let's talk about combustion a little bit. The reason why combustion is redox is because we're having this hydrocarbon fuel. Remember, combustion is a fuel that you add oxygen to. Those are the key parts of being a combustion reaction. And then often the products are oxidized products of this fuel. So carbon here turns into carbon dioxide, hydrogen here turns into water because of this oxygen inserting itself there. Okay, so these are often combustion products, or CO2 and water usually. And then also, how do we know it's oxidation? Let's take a look at this oxygen. In its elemental state, it's 0. Anything by itself as an element has an oxidation state of 0. When it combines with carbon, though, now it's in a compound, it's going to turn into -2. So just like when it becomes a charge, okay, even though it's a covalent compound, it's not really a charge. It's what we call oxidation state. So these oxidation states, there's just a way that chemists account for electron transfers. So this guy goes from 0 to -2. Is that oxidation or reduction? Okay, so back here, showed you my number line. 0 to -2 is going down, so that's called reduction. So it's going down in positive charge, or it's gaining negative charge. So oxygen is getting reduced. That means this fuel is getting oxidized. And I can clearly see that because carbon combines with oxygen, it's getting oxidized. Hydrogen's combining with oxygen, it's becoming oxidized. So the fuel is getting oxidized, and oxygen is getting reduced. So that's why this is considered a redox reaction. Along those lines, you can think of redox in a different way. You can think of redox as oxidation, meaning loss of electrons. Instead of thinking loss of electrons, we can think gain of oxygen or loss of hydrogen. So oxidation is gain of hydrogen. This fuel gained hydrogen. This fuel gained oxygen. Gain of oxygen is oxidation. Okay? Reduction is a gain of hydrogen or a loss of oxygen. So you could think of this O2 when it turns into CO2, or O2 when it's gaining hydrogen to form H2O, or it's also losing oxygen because you have one oxygen here. So you can think of this process as being reduction. So reduction is gain of hydrogen or loss of oxygen. So these are just general ways that you can think about it, especially in biology or organic chemistry. So down here, see these organic compounds? What's happening here? We have CCO and we have CCOO. We gained an oxygen. So what is this called? Oxidation or reduction? Gain of oxygen is an example of oxidation. So this is oxidation. And this is actually what happens with wine. Wine has alcohol, which has aldehydes, and these aldehydes over time turn into vinegar. So this is in vinegar, acetic acid. So that's wine getting oxidized. Okay, let's take a look at this one. We have CCO and we have CCO, but we have one H here, and now we have two H's here. So this is a gain, this is a gain of hydrogen, because I gained this hydrogen right here, and I gained a hydrogen here, although this one doesn't technically count. It's this guy. And I'm also reducing the number of CO bonds. So I'm going from a double bond to a single bond. Usually that's also an indication. So this one's an example of reduction. And those are the symbols. Oxidation is O in brackets, reduction is H in brackets. So that helps you also remember, okay, gain of oxygen, gain of hydrogen. In biology, we have a cofactor. These are molecules that are good at gaining or losing electrons. So NAD plus turns into NADH. So what does that mean about NAD plus? Did it get oxidized or reduced? So look at the difference here. We gained an H, and gaining an H is reduction. So the answer is reduced. So NAD plus turning into NADH, that's an example of a reduction. And you see that a lot in biology. In a combustion reaction, a fuel is oxidized by this oxygen that's present. Which reactant is being oxidized? Well, they just said the fuel is oxidized, and we went over this example earlier up here. A fuel is being oxidized, so that's this guy. Which reactant is being reduced? It's the other one. Oxygen must be reduced. The oxidizing agent is the thing that got reduced. Remember, it's the opposite. So the oxidizing agent is O2. Does that make sense? Oxygen is good at oxidizing things, so it's a good oxidizing agent. And that makes this a reducing agent then.